asked by a couple of people to sort of elaborate on this business of divide and conquer. So what I can do is give you some problems. Because then you can divide and conquer, because then you will never forget. If I do it for you, it will be a cultural experience. That's it. And I'll do that. I'll do that after this and before or during when we are on a walk together. I'm sure we can construct problems with that. So what I want to do is switch to trying to understand the questions that were raised. I'm not sure I'm going to give you any answers, but I'll raise even more questions. And these questions, hopefully, if we try and handle at some level, you may get an idea of what it is to understand dynamical phenomena in hydrodynamics, where the nonlinearities are important as well. So the equations that I've written down before have been erased, but there's a fundamental nonlinearity in hydrodynamics, which is this convective or advective nonlinearity, the U-dot gradient, which is the source of all difficulties, most difficulties, I would say all difficulties of the subject. The other difficulties, of course, the fact that fluid doesn't slip when it's in contact with a solid. So those are the primary interesting bits that go into a mathematical theory which give rise to the difficulty in trying to compute things like drag. Now if I look at this calculation, which is a laminar calculation, or nothing to do with a calculation, I essentially just did a scaling estimate for the drag force on an infinitely thin plate, we made a fundamental assumption. We made many assumptions, but a fundamental one was that it was a steady problem. I waited until all the things that had to happen until I reached the steady state happened. And so the first question is there a steady state? And I suggested, our estimates suggest that there is a steady state. You've got to do a little more to actually show it. But then there is a second question that immediately follows, which is that steady state stable? Okay. And stability is a tricky business. So stability and instability is a tricky business because I have to ask, to what? Is the system unstable? To what? Changes in boundary conditions, changes in the parameter in the equations, changes in the equations themselves. You can have all kinds of stability. So in mathematics, for example, there is this notion of structural stability. I can never write an exact description of any physical system, and therefore if I change the equations themselves, do I essentially get stability of the phenomenon? In our case, in our context, we're going to focus on stability in a much simpler and humbler setting, although I will tell you about the others. I'm going to ask the question in the context of linear stability or instability. And that simply means that I have small perturbations that I add on to all the variables or some of the variables, for example, the velocity, the pressure, the height of the interface, all of the above. And I then ask whether or not that system will relax back. Okay. So there are three possibilities. One possibility, it relaxes back, gets damped. So for example, if I'm thinking about the interface between air and water, I perturb the water interface, it relaxes back. Stable, asymptotically stable if you want, because not only does it relax back, eventually it completely shuts down because there is viscosity. The other possibility, which is the reverse problem, water above air, and then it's unstable because it runs away. And there's a third possibility, which is neither, where it just remains forever, oscillates forever. It should be a conservative system. That's a very hard problem to understand, because that means you have a lot of what are called neutral modes. So how do we understand linear stability or linear instability? We basically introduce perturbations. I'll do it with words, and then I'll start putting down a very simple equation. So do perturbations grow, decay, or remain neutral? And I can ask whether the perturbations grow, decay, or remain neutral in time or in space. What do I mean? If I have an interface, again I'm thinking about the air-water interface, I introduce a perturbation. I can ask whether the perturbation grows at that location in time, or decay at that location in time, or just oscillate. Or I can ask whether or not that perturbation advects, moves out, and starts to grow. Okay. So in physics, what people would call a perturbation which grows in time at a particular location. So whether I have absolute or absolute instability, or absolute instability or absolute stability. That would correspond to the notion of essentially staying in one place and then asking whether the perturbations grow in space in time. The context of whether they grow or shrink in space is associated with what's called a convective stability or instability. Now you may ask, it doesn't really matter because I'm essentially able to move from one to the other by just running, just changing my frame. Okay? But a lot of practical problems that change a frame matter. So I'm thinking about a hydrodynamic situation. It does matter whether it's going to rain in Denver. I don't really care whether that instability is going to be advected, that is to say whether it's moving down towards the west or the east, or whether it's actually going and shrinking at that particular location. So even though there is a way to go from one to the other through a change of frame, for a lot of practical reasons, you have to ask the question whether there is an absolute instability or whether there is a convective instability. Does it grow at one location? Does it shrink at one location? Or does it essentially advect as we move downstream? So that's one sort of classification. There is a classification which is also important. By the way, there's one more problem for you, everybody. In the context of dimensional analysis, I'm sorry, I should have mentioned this at the beginning. So I told you about an explosion of an atomic weapon. There are also explosions underground, much harder to analyze, and there are explosions underwater. And so here is the question. I have an explosion underwater at a depth h, and the explosion energy is E, and I'd like you to calculate the frequency as a function of the energy, density, gravity, and h.
Frequency?
Sorry. Frequency of the bubble that is actually created by this explosion.
It's not a sweating.
Actually, if it's at depth, it will oscillate. If it's at the surface, it won't oscillate. At the depth, it will oscillate because you have essentially an overburden, which is your rho gh. So it's going to grow, and then, if I'm very close to the surface, you will just rupture through. But otherwise, in fact, you can have oscillations. Okay. You have to trust me on that. I can't do the experiment, and I don't think anybody over here wants to do the experiment. All right, so sorry, that's an aside. And I'm going to now erase this, because I need the space. So if I think about stability and instability, you know from particle mechanics how to deal with it. And I've drawn a picture for you. In particle mechanics, for example, if I had a particle at the bottom of a quadratic well, then it's stable in the sense that and I have a little bit of damping on the particle, if I basically move it away, it'll come right back. But suppose I write down the potential V as having a quartic part and a quadratic part, quadratic and a quartic part. That's true when alpha and beta are positive. That's what it would look like. But as alpha changes sign, and everybody over here has seen this in the context of phase transitions, but I don't really care about that context. I really want to talk about it in the context of a particle. As alpha over beta changes sign, or in particular over here, when alpha becomes negative, what happens? Well, that stable point becomes unstable, and instead of having a single minimum, I have two minimum. Sorry? Alpha. Sorry, I meant that. I'm sorry. Question, what happens? Okay. Yes, when alpha is negative, you essentially have a stable point which is being converted to an unstable point and two new stable points which appear as solutions of dV dx equal to 0. Okay, so there is a parameter or a ratio of parameters over here, and as I tune this ratio of parameters, I essentially switch stability. In hydrodynamics, there are lots of parameters. Okay? In the simplest setting, in bulk flow, I told you about one, Reynolds number. And there's a very simple question that you can ask, the answer to which is still unknown. I take two flat plates, I move them past each other. Two-dimensional problem. Okay? When I move them past each other, I can essentially move into a frame where one of them is fixed, so it's effectively only moving one of them. And so I have a velocity profile which would essentially look like it's just a linear profile, u varying linearly. But now, so that's my base state. And u varying linearly in depth with the height allows me to calculate a Reynolds number, which is based on the height, the velocity of the top plate, and the viscosity. And now I calculate the stability of the full Navier-Stokes equations, 2 perturbations. So I will write it down. I won't do this, but this question has so 1 over RE times minus grad P plus, now in scale form, I don't have any parameters, divergence of u equal to 0. The steady state, this term is not important. You can calculate steady state with the nonlinearity, but suppose I ask for a minute that I don't even care about that. I balance these two. I have that my state corresponds to a macroscopic u, a height h, and that's it. That's my entire problem. So now I ask the velocity u in the interior is some function of space and time. In fact, time is not important, it's steady, but it also has a parameter. Okay? Does this solution, u varying linearly, remain stable for all values of the parameter? The answer is linearly, this is an old calculation, linearly it does. So you can go from Reynolds number equal to 0 all the way to Reynolds number equal to infinity, it does. So there is a second notion of stability, which I again only want to mention, but I won't go into, which is the notion of a nonlinear instability, which means that I'm no longer looking at situations where the perturbations are small, infinitesimally small, but I'm asking whether large enough perturbations, and so large enough means compared to something else, and I'll be precise in a minute, but when large perturbations grow while small perturbations decay. That's a nonlinear instability. That's a much harder notion to essentially get a handle on, and the reason it's a much harder notion to get a handle on is because I need to essentially do a nonlinear calculation to understand that. What does this mean in the context of things like what is familiar to people over here? It's associated with, for example, a nucleation or a phase transition. So if I have, for example, a nucleation of a crystal from a liquid, or a liquid from a gas, I have to pay a certain amount of energy in order to get a bubble of a critical size, which is associated, for example, with the bulk energy and the surface energy. So until I get a bubble or a drop of a particular size, you won't grow, because the surface energy is just too large in order to pay a penalty for very small objects, because surface is much larger than volume. So it's very difficult to nucleate until I get a critical size, and then I grow. Okay? So that means I essentially have to have a large enough perturbation. Somebody has to give me a seed, or something has to happen in order for me to get a critical size. Only then will I grow. And the same notion, rather than thinking about it in terms of phase transitions, if you think more generally in terms of stability, is this notion of nonlinear stability or nonlinear instability. When I have a perturbation which is large enough, will it grow?
You also have thermal fluctuation. You can have a fluctuation.
You can, yeah, in these hydrodynamic systems on the large scale, presumably thermal fluctuations don't play too important a role, but on the small scale, presumably they will in the nanoscale, for example, microfluidics, yeah. But I'm not even talking about thermal fluctuations at this point. Those, of course, are very important in phase transitions.
Well, like a nucleation theory.
Yeah, exactly, where you have indeed. Okay, so I want to emphasize this, but that's it. I'm not going to say anything more about it, because this is a subject, again, which is, it's much more than what I want to do. Instead, I want to focus on, so having told you about the distinction between linear and nonlinear in terms of large amplitude versus infinitesimal amplitude, and having told you about the difference between absolute and convective, now I want to focus on only one thing, and I'm going to focus on absolute linear stability. Okay? And I want to do it by first showing you a couple of images and trying to do the experiment that failed just before I finished in the morning. Maybe it will fail again because all of you are watching. And then I'll do a little calculation, but the calculation won't be a formal one. It will be again at the level of trying to understand the physics. First experiment that you can do, I'm sure you've done, you just take milk and drop it in water. Okay? Or honey, or milk is some constituents in milk are slightly denser than water, cream is not. So the milk starts to sink, but it doesn't sink uniformly. It starts to form this extremely complex pattern. You get these mushrooms, the mushrooms then themselves break up. Why is it happening? It's fundamentally happening because you have a heavier liquid on top of a light liquid. Okay? And that instability was first considered in hydrodynamics. Many instabilities are named, as I was telling you yesterday, for the people who first worked on them. And the two people who were giants in the subject, one in the 19th century and the other one in the 20th century, were Lord Rayleigh. I can't help but ask the question. Rayleigh got a Nobel Prize. How many of you know what he got it for?
Linus guidance.
Not the front row first.
Rayleigh get right?
Yeah, think of all the theoretical things he did. He didn't get it for anything like that.
Literature.
Nice try. Now the first row.
Chemistry.
He shared it with a person who got it for chemistry. He actually got it for discovery of argon. He was a theorist who took the experimentalists very seriously because they essentially realized that there was a missing element which was noble when they tried to react everything with everything else. And Rayleigh took the experiment seriously and said there is a gas which is not reactive, and here is approximately what its atomic weight is. And a chemist colleague of his in London essentially said yes, and he did something else, and they shared it. I can't remember the name of the chemist, but they got it together. Rayleigh in physics and the chemist, for something you would not think Rayleigh has his name attached to. Anyway, okay, so Rayleigh, of course, did a lot of things in hydrodynamics, including studying this in the 19th century, and then Taylor recognized that this instability which Rayleigh studied when I have a heavy liquid over a light liquid, Taylor generalized to the notion of a liquid accelerating to another liquid. Rather than having gravity, you have an acceleration. A problem of a lot of importance when Taylor worked on this in the 1930s, 1940s in the context of weapons. Okay, so you have all kinds of issues associated with one liquid accelerating to the other. So his contribution was to generalize Rayleigh's idea. And the first one is called the Rayleigh-Taylor instability. And the second one, it's a picture which I've stolen like almost every image over here from Wikipedia, is what's called the Kelvin-Helmholtz instability. So this is a cloud. It's one illustration, but it's much easier for you to excite it in your bathtub or in your kitchen sink. If I have wind blowing over water, light over heavy, so now it's stable, but now I have flow. So in this problem, I don't have flow. I basically just start with the stationary state. And the notion of stability and instability is fundamentally associated with not only introducing perturbations, as I said before, but also the notion of having a base state. I should have emphasized this. Perturbations about what's called a base state. And this base state, for mathematical rather than physical reasons, is assumed to be stationary. Could be steady. Usually, so stationary or steady. So guys, I'm not going to think about oscillatory states. That's a huge can of worms. And so in the first case, both liquids are stationary. I set it up so that I have a heavy liquid on top and light liquid at the bottom. The second case, where I have a light liquid on top, heavy liquid at the bottom, and then I just drive one of the liquid or the other with a fluid velocity. So the question is, how can we understand either one of these instabilities? And in order to do this carefully, I have to write down the equations that we have over there. It's easiest to do this in the limit when the viscosity is not important. Then I have a balanced, so I have to introduce now a body force, because gravity is important in both situations. So F is rho g, and I now have to ask, when I change a parameter, in this case the parameter is the density difference between the top and the bottom. So this is a, let me draw the picture. I have rho prime as the liquid on top, density. Rho is the density of the liquid at the bottom. Rho prime is greater than rho. And I want to ask what would happen to this interface as, once I've started and prepared it, at time t equal to 0, I let it go. Okay? So here, the notion of the base state is essentially not even relevant. It's simply asking, I started with a time t equal to 0, upper liquid is heavier, let go. The second problem, the Kelvin-Helmholtz problem, has a velocity, also a density, rho prime and rho, but here, rho prime is actually less than rho. Okay? And here, I'm assuming, for example, that I'm essentially blowing wind over water, and I want to ask whether or not I'm going to essentially create that kind of an instability. And the physical picture that I'd like you to have is that if I have an interface and the upper fluid is moving relative to the lower fluid, there's an interface in between, so the upper fluid wants to essentially rotate because you have a shear, and that shear is localized to the interface. In more complicated situations, if I have viscosity, the shear is going to be distributed. So the simplest setting is uniform velocity in one direction relative to the stationary fluid at the bottom, light at the top, heavy at the bottom, and as soon as I try to shear it, it wants to turn over, it wants to tip over. Will it tip over? Now if there is no gravity, what's the answer? Immediately, because there's nothing to restore it. But as soon as there is gravity in the right sign, it's not going to happen immediately, because I have to essentially fight. Okay?
What about reduction in pressure with the moving fluid?
That is going to be associated with the velocity. So
that
that's
is the same effect.
yeah, because I can say the pressure that I have in the implicit limit is going to scale with rho times u squared. So the notion of the velocity, the notion of pressure essentially intermingle with the implicit limit. Okay? All right, so how can we do this calculation? So I'm going to do this in as crude a way as possible. And so for that, I will keep the left side for the Rayleigh-Taylor and the right side for the Kelvin-Helmholtz. Keep leaving my chalk all over the place. Okay. So here is my interface, heavy fluid over light fluid. I introduce the perturbation. Thank you. This is my original interface. This is the height of the perturbation. And I'm going to do a normal mode decomposition, which is the way you would analyze any linear problem which has a dependence in space and in time. So let me say that the height of the interface in 2 dimensions, so it's a 2-dimensional problem, I'm not going to know what happens in the 3rd dimension, zeta of x and t, I can write as a Fourier decomposition like so. Okay? So my spatial dependence is expanded in Fourier modes. My temporal dependence is something that I want to essentially determine. And I want to ask, are all modes, so that's my wave number, are all modes equally likely to grow or not? Or is there some criterion, is there some transition? Okay, so you can do it formally, but you can also do it just by staring at this picture and then computing static. Because this is a static problem, I can compute energies, just like I compute energies for particles. And I ask whether the energy associated with this change is going to be giving rise to a reduction in the total potential energy of the system or not. I forgot to say something very important, that because I'm thinking about the scale, because I'm thinking about this problem on the scale of the container of liquid on the human scale, I also have to worry about surface tension. Okay. Question?
I was wondering if you know how this experiment was performed.
I don't. Yeah. But why? But what is it?
Because when I can't do this with milk and water, like the milk will not accumulate at the top; it will directly fall. No.
You have to be. You can't drop it from very high. That's the only thing, because you don't want impact to essentially make a big difference. So drop it from as close to the interface, because then if you don't, there is an additional complication. Okay. More questions? Okay, so there's surface tension as well. So surface tension is gamma,
surface tension between the milk and the water?
In this case, I'm just going to say one liquid and the other is the interfacial tension. Yeah, between milk and water, exactly. Milk and water and air. Yeah, really milk and water. Okay, in fact, Phil, you bring up a very important question, so I'm going to address that. I think what you wanted to also ask is what happens when they are miscible, perhaps.
Yeah.
Okay, so that's a much harder problem, because now I have an instability associated with a diffusive propagation. And what I erased was I said I'm going to look at stationary cases and then ask what happens. So if I had already a dynamical situation where I have gradual mixing, now I have to ask how do I introduce perturbations on that dynamical state. It's a harder question to analyze. It's not trivial, because I have to ask myself about how growth rates are a function not only of space and time, but of the thickness, which is a dynamical variable. And there is no general theory as far as we know. There are specific instances where you can work through. Okay, so the energy, total energy, so gravitational energy is going to be reduced if I basically make this heavy liquid at the top go down. But then I have a problem, potentially because of surface tension, because my interface, if it's flat, has the least amount of contact between the two. As soon as I deform it, I have to stretch effectively the interface. So I have two energies. And I'm not doing a dynamical calculation, I'm doing an energy calculation. But again, you know that when I think about particles in potential wells, effectively, energy calculation is the same as dynamical calculation, because what's happening is instead of having modes which are oscillatory, I get modes which are growing. Okay? E to the, if I'm thinking about a purely temporal problem with no space, e to the omega t. If omega is imaginary, it's oscillatory. If omega is real, it's either damping or growing. And because it's a real equation, I'm always going to get complex conjugate roots, and so for every positive one, I'm also going to get a negative one, and the growth dominates. So I won't worry for now about that situation. So I won't worry about the dynamic situation, I'll do only the static calculation. So the energy due to gravity is rho prime, reduction, is minus, so it's a reduction if it falls down by an amount which is zeta k, minus rho prime minus rho times g times a characteristic amount of liquid which I am moving over a length scale lambda, which I don't know, or 1 over the wave number. So the amount of liquid that I'm moving is proportional to the wavelength. It's moving an amount zeta k. And the work done, so that's the force, and the force multiplied by the distance is the work done, and that's the work done. Per, now not per, it's essentially integrated over a wavelength. Okay? So, delta rho times g is the weight per unit volume, integrated over a length, weight per unit area, multiplied by this is essentially a weight. But that's also work because I'm doing everything per unit weight. What about surface tension? Well, surface tension, basically, I have to now use Pythagoras' theorem to ask you what is the extended change in length when I go from something which is flat to something which is tilted. So, a crude, very crude estimate of this I can do by looking at, I've drawn a half bottom and half top because it's easier over there. But if I just think about it, so I have an amplitude zeta k, I have a characteristic size which is 1 over k, and Pythagoras tells me that the difference between the length along the arc and the original is square root of 1 plus d zeta dx squared minus 1. Okay, the original length is 1, or really everything is in units of k, 1 over k, so that's the difference in length. And if I do an expansion for a small amplitude, this will give me a zeta x squared, but if I have a Fourier decomposition, it will give me a k squared. Okay, so the energy contribution is going to be plus the surface tension, which is the energy per unit area, but again now everything is per unit length, times a 1 over k, times a k squared zeta k squared. We're writing out this. So what I've done is 2 steps, this is equal to zeta x squared times 1 over k, and if I write it down in terms of the Fourier decomposition, differentiate this with respect to x, we're going to get out a k or an ik, square it, and therefore I get a zeta k squared k squared. So let me write down the energy again. E is equal to minus rho prime minus rho. I'm going to take out the k plus gamma k squared times zeta k squared over k.
There's a G, you have a G.
Ah, there's a g, thank you.
So I don't understand, so in the picture on the left,
Yeah.
the total gravitational energy seems to be the same. You're gaining on the left and losing on the right.
Well, if I have a bump, for example,
So how do you satisfy incompressibility if you have a bump going down? How do you not lose volume?
no. So if I have something which is infinite, okay, and I create a bump, so maybe I'm misunderstanding. I create a bump,
Light is moving up and heavy is moving down.
yeah, because the light fluid is what is going down, exactly what Michael said, the heavy fluid is moving up, so it's not the same fluid. The areas may be the same, but the densities are different,
Oh,
okay?
Yeah, but when you did work, the work is positive when you move up and negative when you move down.
Indeed.
That's different.
Yeah, and you said it's zeta k squared, but it's sometimes zeta k squared and sometimes minus zeta k squared.
Yes, indeed. So what maybe I'm not sure I understand what the trouble is, because if,
If I tell the student asks the following.
yeah,
Potential energy of that part of water increase. Potential
this is
energy
water.
of that.
Remember, this is water. This is air.
Oh, this is the, okay,
Yeah.
other way around.
Yeah.
And potential energy of that part of water decrease. Right?
Yeah.
Potential energy of that part, you have this part of water
Yeah.
and this part of
Yeah.
That's air.
So I'm going to come to that. So what you're saying is it's not clear that it's unstable.
water. That was your question,
That's
right? Whoever asked
yeah.
that question.
No, I'm fine now. It happens more than I'd like to admit. No, I'm
Can I
fine.
continue? Yes.
I don't understand why that zeta k squared but not zeta. So I mean, where does the square come from?
It comes from the fact that I have rho gz is the pressure, and then the work is the integral of rho gz dz. Okay? So there's a half and some, but okay. All right. So if I have my energy now, I can pull out the amplitude square. Makes sense. The amplitude square should drop because it's a linear calculation. I have a 1 over k which is associated with the wavelength. But now I have two terms, one which is independent of k and the other one which is dependent on k. So depending on what k is, this can be positive or negative. Okay? So if k is large, this is positive, so it's unfavorable. K is large corresponds to shock waves. If k is small, potentially it becomes favorable, and the crossover happens when this goes to 0. And all I can really do with the linear stability calculation is to calculate the crossover. You can do a little more than that if you have a little large piece of paper and you can do a perturbation calculation, but I'm not going to do that. I'm just going to tell you about the marginal criterion. So the marginal criterion is associated with these two terms balancing, exactly like what we saw earlier today in the context of energies which scale with different powers of various length scales in that case. Okay? And the marginal criterion is associated with saying rho prime minus rho times g is equal to gamma k squared. And so out comes a critical k, which is square root of delta rho g over gamma. I think. Yeah? First thing, notice that the sign of delta rho is very important. And you know that it should be. Okay? Second thing, K star, or what K star is an inverse length scale. So this is an inverse length. So there is a characteristic length scale. And the characteristic length scale, if I calculate for air and water, rho is 10 to the 3, water is 1, so I forget about it. G is 10, so that's 10 to the 4. Gamma is 70 millimeters per meter, so I'll say it's 100 millimeters per meter, which is 10 to the minus 1. So K is square root of 10 to the 5, which is approximately 3 times 10 to the minus 3. 10 to the 3, excuse me. And so lambda is 1 over that. And so lambda is 3 times 10 to the minus 3 meters. It's 3 millimeters. Okay. I did all this because I've done it before. Okay, I didn't want to write it out, but K star, I'm sorry, I'm going to deliberately use only this side because I wanted the Kelvin-Helmholtz problem there. K star for air water is 3 into 10 to the 3, which means lambda, which is the inverse of this, is approximately, that's meters inverse, and lambda is approximately 3 millimeters. Short waves will not grow, long waves will grow more easily. What's the intuition? Short waves require a lot of curvature, hard, long waves much easier. What is the consequence? If I have a bottle with a narrow opening, it's much harder to empty it, because surface tension essentially is dominant, and the big waves can't grow. So if in particular I have an opening which is less than 3 millimeters, if I have an inviscid fluid, it's not going to essentially have the ability to move out. Long waves will grow. Let me try the experiment again. If there is some way to suppress long waves, then you should have an instability. Okay? So here goes again. Filled with water. Everybody pray. Okay? Probably will not work again. Maybe it will. There you go. So I've suppressed the long waves, and because I've suppressed the long waves, I don't get the instability.
You said 3 millimeters? Or
Yeah. Sorry? What did I say? Suppressed?
No, but your wavelength is 3 millimeters.
I know. So I suppress the long waves, and the long waves are the ones which will grow. And so by having this sheet of paper, I prevent the long waves from
What
growing.
about between 3 millimeters?
Oh,
and
yeah,
5
well,
millimeters?
Give me, okay, maybe I should try with this bottle.
I'm just joking.
And as soon as I remove this, okay. So that's the first very simple estimate. And it also tells you something about stabilization, because it depends on the sign of delta rho. Questions?
The effects for what you showed, are you sure it's this? Because it looks like, I don't have the words in English, but you know the thing you use to, you're in the toilet.
A plunger?
Yes.
Yeah? What about?
It looks a bit like the same effect. Like the force of the water, gravity, maybe bring closer the paper and the glass. That's why air cannot enter.
So then, what we mean surface tension? No, plunger doesn't have suction because. Oh, I see what you're saying, because you're saying there is a little bit of air inside. Okay, but I can do the experiment a little more carefully with no air inside, and it's not going to make any difference whatsoever. Yeah, so suction is, I think, what you were thinking about, but that has no role over here if I just completely fill it.
Okay.
That requires a little more care. Yeah, question?
What was the piece of paper that you were using?
Oh.
Was that just foolscap or?
No, it was something that I took from my hotel. Except it's very nice because one side is essentially wax paper, so it doesn't wet. If it wets, here's a question, another question. If it wets, how long can you maintain it before it breaks? So what do? Well, I have to ask, what is the time scale for the penetration of water through paper? And if I have time at 350, I will try and do that calculation. Okay, not this one, but a very closely related question of how does water move through a sponge? Okay? All right, so I want to now move to Kelvin-Helmholtz problem, but I'll do it much more cavalierly, much more question.
The picture we need doesn't look like
Can you speak up? I can't hear you.
the photo. It doesn't look like it's the I wavelengths which are controlled.
Yeah, okay, excellent. Indeed, what I actually can tell you. So that is because the interfacial tension between milk and water is much smaller than that between air and water. So consequence is that even shorter wavelengths can actually grow. First. Second, I'm observing this well past the onset of the instability. Okay? I don't have pictures, but right now, if you just type when you go home, hopefully not in the next hour, just do Rayleigh-Taylor instability and look at numerical calculations. It's an unbelievably hard problem to solve numerically, even numerically, never mind anything else, once you go past the instability. And in particular, that's associated with the fact that if I have a very, very small interfacial tension, I start getting very fine features which start to grow. Okay? I'll stop there. There's a huge amount of interest in that problem, but very, very little can be done except in the context of heavy numerical simulations.
So it's just a comment. So to show, because here in your demonstration, actually you not only suppress the long wavelengths, also suppress short wavelengths.
Indeed.
So it's another demonstration to show that is you have say a metal film that with a millimeter size holes.
Pores, exactly. And I increase the size of the pore, and there's a critical size above which will become unstable. Exactly what you said. Indeed, yeah. That requires, again, a little more work. But yeah, absolutely right. In order to actually make this really watertight, literally. Okay, so Kelvin-Helmholtz problem. Difference is now the upper liquid is actually less dense than the lower liquid, and the jargon is it's stably stratified, and that's unstably stratified. And you want to ask the question, now what happens? Okay? If I'm thinking about very large-scale phenomena, such as associated with clouds and wind on water, surface tension may or may not be important. And I'm going to do the calculation without surface tension. I think of large-scale phenomena. But you'll see in a minute that it will actually give you a result which is not, which you, I guess you'll make your own mind up. Okay, so I'm going to do this much more dirtily. I won't even write down the energy balance. I'll just tell you what the two energy scales are and basically just do it. Okay? So one energy scale is related with the fluid velocity. Okay? I've written it down not as an energy, but an energy density. Energy per unit volume, rho u squared. And the other is our old friend, rho prime minus rho times g. And then if I just compare it with that, the energy density is 1 over k. Okay, a characteristic length scale multiplied by g multiplied by the difference in densities. You can do the whole thing again with amplitudes, with linear stability, with a zeta k squared, and so on and so forth. But at the end of the day, you know that essentially I'm going to still get, again, a zeta k squared multiplying both these. I'm going to get a 1 over k, but again, I can pull that out. And so instability and stability is going to be determined by just this balance. Okay? And you actually even know how it's going to work, because if u is 0, it's stable, stably stratified. So the condition for instability is this. Okay. Notice that the condition for instability.
Which one is rho and which is rho prime?
Oh, I'm going to take the limit where rho 1, I'm going to say rho minus rho prime is small compared to both rho and rho prime, and so I'm not going to distinguish between rho and rho prime when I write down rho, but I will distinguish between them when rho minus rho prime comes in. It's a little more messy. I'm going to get actually, if you do the calculation properly, I'm going to get a rho 1 squared, rho prime squared minus rho squared. On the right side, I'm going to get a rho 1 times rho 2 or something like that. And in the limit, when the densities are almost the same, this is the limit which I'm thinking about. Okay?
What is this comparison of?
It's a comparison of an inertial pressure and a gravitational pressure. But really I can convert this to a work argument if I write down a normal mode expansion for the interface and then calculate growth rates. I mean, I've just done it in terms of energies.
And the right, you just put just a simple thing. You mean probably rho minus rho prime, right?
Do I?
You
I'm
don't
sure
mean
you're right,
negative,
because I want this to be positive. Yes, I do. Yeah.
What's confusing? Why isn't there an analog of C that appears? Why isn't there an amplitude?
There is.
Well, this is the thing that multiplies C squared.
Exactly. Both the terms will multiply the zeta k squared. Yeah, so I said I'm not going to do this as carefully. I've just written down the terms which appear. And I've written them down really by basically asking what are the dominant physical effects. One physical effect is that of inertia, and the other physical effect is that of gravity. Okay. So really, again, if I want to think about it physically, I want to try and deform the interface, but in order to deform the interface using hydrodynamics, essentially get a pressure, I have to lift some liquid. And how much do I have to lift depends on the density differences. And so all I'm doing is comparing those two energies. That's all, okay? Okay, so again, this gives you a critical value of K. So K greater than rho minus rho prime G over U squared as I go further and further away from the instability. And notice that unlike in the original problem, not the original problem, unlike in the Rayleigh-Taylor problem where long waves are more likely to be unstable, here short waves. For a given U above criticality, it's short waves which are more likely to be unstable. And again, if I think about it physically, it makes a lot of sense because a long wave inertially is very hard to excite and gravitationally is also very hard to excite, while a short wave doesn't cost me very much. So there's a problem. In principle, if I give you a very large U, then, sorry, not a very large U, if I just give you some U, no matter what it is, there will always be a wave number above which I will get an instability. In fancy terminology, you have an ultraviolet divergence, but over here what this is saying is that shorter and shorter waves essentially start growing faster and faster. How do we deal with that? There's a cutoff, because I did not put surface tension over here. If I put in surface tension, I'll have to redo the calculation, and then I will find there's a short wave cutoff. Again, below a critical wave number, which is essentially going to be exactly the same wave number that I calculated over there, balancing surface tension and gravity, waves won't grow. Above that, they will grow, and again, below a certain second wave number, which is associated with gravity, again, I don't get growth. So there's a window. Okay? Leo?
But the Rayleigh-Taylor, do I need to think about free surface above the denser fluid?
What I told you about is two half spaces. If I have a second free surface, of course, that's forced by what happens at the interior free surface. Much harder question. Because that surface is stable, if I am thinking about water, air, and then air outside still. And so I have to worry about what's happening there, which is completely, in fact, it's stable. But it's going to be dragged in as I have an instability growing at the interface, and that's well beyond what I'm able to do at this point. Okay? Okay, so every fluid problem can be cast, even though I chose these so that I can actually say something about them in 15 or 20 minutes. Every fluid problem can be cast in terms of saying what a base state is. Here, the base state is one fluid moving over the other with some velocity. Over there, one fluid above another. And then asking how perturbations grow or shrink. If I want to go beyond the linear calculation, it's not easy. It's possible, it's not easy. I'm going to just stop there. You can either do a numerical calculation. There are some approaches which do an amplitude expansion, but this is not the place for me to do that. So what happens if I go far above onset? Okay. Like here. I mean, this costs a penny, and with $1 million, you can't on a supercomputer solve that. What happens if you go far above the instability? What you can see is that you start with big structures, and that's why this picture is also so beautiful. You start with these large scale, big blob, and you start to get smaller structures. The big structures form small structures, the small structures potentially form even smaller structures. And so one way to address that is not to solve the problem, but to make a poem about it. Okay? And a very famous English Quaker scientist, who was one of the first people to actually even dare to compute the weather, a man called Louis Fry Richardson, in the 1920s. He, in the First World War, was an ambulance driver, His religion prevented him from actively taking up weapons, but it was okay for him to help in the cause, so he was an ambulance driver. Soon after the war, at that time he started working on weather prediction. He was also one of the first people to recognize the importance of fractals, which we've heard a lot about. And soon after the war, he essentially stopped doing anything to do with the weather, but he was interested in turbulence, and he made up this lovely ditty, which is actually a takeoff on Gulliver's Travels, Jonathan Swift, and he said, Richardson said, that big worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So in a poem, essentially saying what seems to happen in problems associated with the big unsolved problem in hydrodynamics, turbulence, where you're dumping energy on the large scale, or over here, in a much more humbler setting, you basically have set up an unstable situation, and you're starting to create smaller and smaller structures. So the idea that Richardson had is that on the big scale on which you're dumping in energy, gives large-scale motions, vortices, for example, and these vortices break up into littler vortices, and so on and so forth, until dissipation essentially takes away that kinetic energy, converts it to heat, on the micro scale, because dissipation is molecular somehow. Question?
So why is descending droplet is unstable if it just slowly falls down in that case? You're saying there's going to be another...
Because so it's much more complicated over there than what I was going to tell you about turbulence, because you're entraining fluid, you're slowing it down, you're also diffusing. So if I'm in inertial regime, so imagine that the fluid is falling, it's pulling liquid, but it's also trying to accelerate fluid in front of it, so it starts to flatten out. So now you have another flat interface which starts to develop. That flat interface can become unstable. Now you get smaller mushrooms, and if you should just try it with milk, literally you will see a big mushroom, it starts to spread out, you'll see little guys fall off. I mean, in words I can say all this, but that's about it. Okay, so what can you do? What can you do beyond Richardson's rhyme? 75 years of work, probably one of the most robust results there is due to a Soviet-Russian mathematician, Kolmogorov, using dimensional analysis. Very, very beautiful use of dimensional analysis, but like all questions that you address using dimensional analysis, it has to be followed up by a lot of work to justify it. And 75 years later, people still argue about how to derive that result from the real equations. Okay? So I'm not going to try and get into that argument. I'll just tell you the assumptions and I'll tell you the result. So it's a very, very nice result. And it's approximately correct. And I'll tell you in what sense it's approximately correct experimentally. It has not really rigorously been derived from the Navier-Stokes equations, although with some approximations, people can massage out things which are close to it and almost there. So, question that I raised is the question of what happens far, and I'm being sloppy in saying all of far from onset instabilities are turbulent, but what happens far from the onset of instability? What is turbulence? Well, it depends on who you ask. I'm not going to answer the question, I'm going to draw it. Okay. That was what Leonardo did when he basically first started thinking about hydrodynamic vortices and hydrodynamic turbulence. So essentially, I'm going to call turbulence a disordered state, but it's not so disordered to be completely random. There is structure. And the hard question that people have been struggling with is trying to understand at what level there is structure. If I look at velocity correlations, if I look at vorticity correlations, if I look at it, depends on direction, depends on position, all those kinds of things. So I'm not going to essentially belabor the point, except to say there is some structure in something which looks tremendously disordered. And Kolmogorov recognized, he knew about Richardson's work from the 1920s or 30s, I can't quite remember. Kolmogorov recognized that this is an interesting, a beautiful problem, and he made some dramatic assumptions. So let me list them. I want to make sure that I list them carefully and correctly. He said that I want to think about a system which is very, very large compared to a scale which I'm going to define in a minute, but just for now it's large. So he said that on a certain set of length scales, this system is statistically isotropic. The paper was about 2 pages long, 1941, his first, and then he wrote something following up almost 20 years later. So the system is statistically isotropic, so no orientation dependence. It's not homogeneous, of course, because you have all this structure in it. These are the assumptions. The second assumption that he made was that there is a characteristic length scale, which is now known as the Kolmogorov scale. And he said there is a characteristic length scale associated with this picture of being statistically isotropic. So I'm dumping energy on the large scale. I create structures on smaller and smaller scales. And I suck out energy on the small scale associated with viscosity. Okay? So in between, I have energy which is moving down in length scales. And if I'm moving energy down in length scales, he said that I don't want a source or a sink anywhere in between. All the energy is gradually just moving down from the large scale to the small scale. So therefore, I have essentially a rate at which I'm sucking out energy at the bottom on the small scales and dumping energy in the large scale. So there must be an energy dissipation rate. In particular, there's an energy dissipation rate, which is an energy dissipated per unit mass. Okay? And I'm going to say that's a constant, because that's the only way to maintain a statistically steady state. Because if I'm putting in too much or I'm taking out too little, it's not going to be stationary. So he said that there is an energy dissipation rate which is epsilon naught, and it's a constant. And energy dissipation rate is already per unit mass, so it has dimensions of velocity squared over time. So it's a power. So energy is proportional to rho u squared, divide by rho, it's u squared, and the energy dissipated is just u squared divided by time. Okay? So this quantity has dimensions of u squared over t, and u squared over t has dimensions of L squared t to the minus 3. And he said that quantity is a constant. Okay? Now,
So why is the mass out? I didn't understand that part.
so rho u squared is I should have said this is always for an incompressible liquid. So it's an incompressible liquid, density variations are unimportant. I'm simply talking about how energy is moving down. I'm sucking out energy at the bottom, so therefore the only energy scale is essentially specific energy, rho u squared divided by rho. Okay? That has dimensions of L squared to the minus 3, and Kolmogorov defined a length scale, which I'm going to call Lk. How can I construct a length scale from epsilon naught? And the only parameter which is there is a viscosity, kinematic viscosity. Okay? So Lk, kinematic viscosity, has dimensions of L squared t to the minus 1. So I can construct a length scale from nu and epsilon naught. First, by taking epsilon naught, which has L squared, t to the minus 3. So I better have divided by nu cube. Is that right? Do we have that right? Nu cube, epsilon naught over nu cube is 6, 4, so it's the other way around. Nu cube over epsilon naught, that's L to the 4 to the 1/4. Okay? So this length scale is the length scale associated with how energy is coming down from large scales and then sucked out through dissipation, heat, because that's viscosity. Okay?
So is epsilon not universal constant?
Yeah, so that's the assumption. So associated with the statistical isotropy, the second assumption is that this is universal indeed. That's the second assumption. I should have explicitly said that. Okay?
What do you mean by universal?
doesn't depend on the details of how you're driving the flow on the large scale. It's simply associated with how energy is cascading down for a simple fluid. That's it.
But it may depend on the fluid in detail.
In the fluid, in what sense? Because the fluid is completely defined by rho and u. Mu, sorry, rho and mu or rho and mu, yeah. That's all that I have, because I have no boundaries. I don't have anything else, because I'm... Okay?
So even you have velocity in there, you can still call it universal?
No, because it has dimensions, so I wrote it down as a velocity, but that velocity is a function of scale, that's the point. Okay? The velocity of the vortices, the energy, is essentially a function of scale. So all these vortices, effectively what I'm telling you is that I don't care what I'm doing on the large scale, as long as I'm dumping energy, and I'm not going to tell you about what happens in detail on all the intermediate scales. Then I go to the smaller scale and I suck out the energy over there and convert it to heat. Okay, so the first thing is, I have to say, if I want to say something, it's statistically isotropic, it doesn't depend on orientation. Second thing that I'm going to say, that's what Kolmogorov said, is that I'm taking out energy at the bottom, and I'm going to take it out at a rate which is exactly what I basically am feeding from all the other scales, and they just cascade down. But there is a lower cutoff, that's the important thing. And that lower cutoff is associated with molecular viscosity.
Wouldn't that be fair to say that the amount of energy you take away at the bottom must be the same as the one you...
Indeed, but the length scales are different.
Length scales are different, but the value of epsilon naught shouldn't be governed by how much you input.
At steady state, no, right? Because I'm just putting in whatever I'm putting in and then taking it out. If I have reached this isotropic steady state.
So yeah, so the question is, what does epsilon naught depend upon? It depends on some molecular quantity, and it depends on something like the thermal conductivity.
He didn't say.
Yeah.
Okay. Yeah, and so the question is under what conditions, which is what you're really asking, can the equations from which we have derived all the things that we have, and Navier-Stokes, give rise to epsilon naught to be really a constant? And the answer is that it's a huge mess. There are some very, very technical, specific conditions that you need in order for epsilon naught to be approximately a constant. I'm telling you, this is the assumption. Right now, it's an assumption. At least Kolmogorov assumption.
But sorry, but we're still trying to, if you're driving harder, let's say at long scales, at large scales,
Yeah.
for fixed viscosities,
I'm going to say that there are enough scales that the difference between the smaller scale and the larger scale is so large that I'm going to look at it. So I'm going to maybe if I make this precise in a minute. So let me just say one thing and then you can ask the question again. So I said there is this characteristic length scale which I can construct if epsilon naught is a constant. And now, on scales which are much, much smaller than the system size, but much, much larger than the Kolmogorov scale, the system is self-similar. Okay? So the three assumptions, and then he calculated what would happen to the energy spectrum in that scale, in that zone. So it's a self-consistency. I check, I look for a case. Actually, he didn't. The honest answer is the entire argument is really just more or less this. He built on this much later, but on length scales which are small compared to the system size, but large compared to Kolmogorov's size, energy is just cascading down. There are no additional mechanisms of dissipation. Just sucking out energy at the bottom, putting it at the top.
is this dissipation on the intermediate length scales?
The only dissipation is, well, so in reality, I mean, dissipation will arise every time I have interfaces between, for example, vertical structures, all these structures that I've drawn for you.
No, but in his model.
He never said anything more. There was no real physical picture beyond what I'm telling you. Okay? And in this scale, there are many ways to essentially tell you this result. He asked, what is the energy spectrum? E of k as a function of k. Okay? The energy in particular wave number, which is now telling you something about the structure, at least at this crude scalar level of how much energy there is stored. Okay? And this result also comes from dimensional analysis, because the energy associated with a particular wave number, so energy again, specific energy goes as u squared, and E of k is an energy between E of k and E of k plus dk, so it's energy per unit wave number. That's what this has dimensions of. And this has dimensions of u squared is length squared, 1 over k is length cubed, t to the minus 2. Okay? So how do I construct from epsilon naught and k dimensions of E of k? And the answer is, I'll write it here, E of k is k to the minus 5/3 times epsilon naught to the, so I want to get a minus 2 here, and I start out with a minus 3, so it's probably to the minus 2/3. Yeah. Okay.
It's supposed to be at k equals to 1 over lk, it's supposed to be 1.
Say that again. Ask that again, please.
K supposed to be at k equals to 1 over lk.
Exactly.
You get 1?
No. So wait. No. So I'm not sure. So at
I
k,
put on to very large k, the largest k possible. And
if I
then
put the
1 over
largest k, so I put largest k corresponding to
Yeah.
lk. I will get E of k to be,
There's some simple interpretation.
I'm sure there is, but I don't see it immediately. You probably can see it from further back.
I don't see it.
Okay, but anyway, so I want to point out, so there are a lot of questions, and that's good, because in fact, all those questions are associated with questioning the three assumptions. And all I want to say is that you should question those three assumptions. Experiments suggest that over about between, I don't know what the recent thing is, about 4 to 5 decades in K, you do see something which looks like a minus 5/3. Now actually with Leo's question, Phil, your question and other questions over here, presumably that you haven't asked, are associated with how do you derive this systematically starting with Navier-Stokes equations? And the answer is, it's really not completely clear. You have to make very strong assumptions about the kinds of structures and the kinds of interactions. And I'll just leave it at that.
So no limit, there's no solvable.
There is no not that I know of. Yeah, question?
A question that doesn't question these assumptions. Why did he go for a length scale? Why not a time scale, characteristic time scale?
I should have said this. Statistically steady isotropic, statistically steady. So you are thinking about a much harder problem, which is associated with what happens to transients. Okay? The easier problem always is the steady state. So you can ask the question, what happens if I suddenly ramp up or ramp down? I don't know.
So where specifically did you use the isotropic assumption?
When I actually did this, I never did explicitly, but the idea is that I have basically no dependence on orientation, and that is associated with ignoring the detailed physical picture that everybody draws, where you have very strong orientational order, because that's essentially what a vortex is. And that's all gone, because I'm sort of just, it's a hairy ball, and I don't worry about any of the detailed physical picture that I actually have. And there's a whole subject, so I should tell you what the current state is. So the whole subject is now trying to understand, there are two questions. One is this statistical mechanics kind of question, which is how do I derive this? The second question is there any model? The second question is trying to understand how these structures, and there's a general, rather than thinking about vortices, they're called coherent structures. So structures which have some sort of coherence come and go. And they come and go, they are transient, so this comes back to your question. You know, is there a transient dynamics? And there almost certainly is. How are they created? How do they interact? How do they disappear? A lot of computational horsepower is spent on that, trying to take from that and say something about the orientation distribution or lack thereof. Don't know. But that's where we've ignored this physical picture, even though in some sense it essentially is what drove, or when I say we, people who studied this, drove the original thinking. Okay? All right, so I have 20 minutes.
Is this supposed to be true for incompressible fluids?
Yes,
or?
sorry. So this is all under the assumption of an incompressible Newtonian fluid. As soon as I start moving away from it, we don't know. Well, there are some things which are known for stratified turbulence, okay, which is very relevant for things on the scale of our planet. And there are some things also known for turbulence in rotating flows, also very relevant for our planet. But this is a result which a lot of people spent time thinking about because it looked very simple and very, very seductive. You know, no boundary conditions, dump energy on the large scale, suck it out at the small scale, presumably you can calculate things. But it's turned out to be notoriously intransigent.
So could you please label the LK on your physical picture?
Physical picture, you mean this?
Yeah.
The smallest scale that I have, I don't know. No, it's not very meaningful. Maybe I'll do this slightly differently. I'll label it here. So I said Ek as a function of K, but I never completed that picture. So I'm putting in energy on a particular scale. And then Kolmogorov's calculation said this is a log plot. There's a minus 5/3. And then something else happens here. And this something else is LK inverse. Okay? And this is the system size. Big N.
Can you
Okay?
give us a sense of that size in a normal liquid? Of that, what that LK actually is, if you look at this energy size?
Yeah, okay, so that means I need to know epsilon naught, and I can't remember what the
I
actual...
mean, does it roughly correspond to some sort of molecular like?
It corresponds to, in very strongly driven systems, so such something in your washing machine, for example, but on a large scale, it would correspond to something of the order of fraction of a millimeter. Depends on how
So
hard.
much larger than molecular size.
Yes, yes, it can be.
But it should depend on Reynolds number? Reynolds number? That inertial rate?
Well, Reynolds number, but what length scale I'm going to use? The system size, presumably.
Right.
So
You want, on the scale of the system size, you want Reynolds number to be...
it's large, very large. Yeah. Yep.
Two-part question. Can I get you to define turbulence? And the reason I'm asking is because this seems like very general. And maybe there are systems without even flow, you know, where you don't have any viscosity and you can talk about turbulence.
Yeah, so okay, so I mean, I did it using words, I didn't do it mathematically. And so I said that it's a state of a fluid which is driven, where you have what seems like a lot of disorder, but nevertheless, if I look carefully, I do have some structure. And to say more than that, I don't know that I really can. I mean, I can define it in terms of correlation functions for the velocity, the orientational component, I mean, things of that sort, but more than I can't. But I will address the question that you raised, which is it can be there in other systems as well. All right. So, in fact, if I have microscopic flows, so low Reynolds number flows, but with elasticity, so polymer flows, people have talked about what they will call elastic turbulence. And what they really mean is, again, you have disordered structures on multiple scales which are talking to each other. That's what they really... Yeah, please?
Is the transition of energy from large scale to small scale, the way that you described, is this also part of the definition? Is it part of turbulence?
Yes. That is to say you have many, many length scales. You are driving on one scale, and then you are getting all kinds of structures which form dynamically as a consequence. I mean, you do see this in different systems. You see them in plasmas, you see them in elastic liquids, which you will hear a lot about. I don't know about the context of turbulence, but the first place where it was sort of crystallized as a question was this. And it's still pretty much an open question.
So what about liquid helium?
Okay, so there was originally a lot of talk about, so how are you driving it? So are you driving it by basically flow, or as many of your colleagues do, by using heat?
Yeah.
Now that's a different kind of turbulence, because it's a turbulence associated with now asking how quickly or how slowly does heat get conducted from one boundary to the other. So Phil's question is the following, which is very relevant to our planet again. So our planet has an atmosphere. The atmosphere is not heated by the sun, it's heated by the earth. Okay, so the earth gets hot, and then the earth heats up atmosphere. So now you have a problem because I have hot gases lower down and cool gases at the top. Also an unstable situation because now hot gases want to rise and cool gases want to come down. So the question then you can ask is there is instability there as well, and it's also known as the Rayleigh instability, but the next name that you add is Bénard, who was a French scientist who more or less simultaneously did experiments. Rayleigh started to understand it theoretically. And the question that Phil's asking is, what about turbulence there? So turbulence over there is asking how is heat transferred from the bottom plate to the top plate, for example, in the context of helium. So there, the parameter is something else. It's essentially a ratio of thermal diffusivity, buoyancy, and momentum diffusivity coming in some particular. And there too, there's been a lot of work which shows that you get beautiful power law scaling over 6, 7, 8, 10 orders of magnitude. And there too, there is this question of, is there an ultimate limit like this? The suggestions are maybe, but then people argue about exponents because you have exponents which switch as you move from one zone to another, but the zone in decades is rather small, so I don't know.
And for this particular case you drew there, what happens with Reynolds number if you think about Reynolds number as a function of k? Is it decreasing?
The Reynolds number is naturally decreasing as k increases because the length scale is decreasing.
But velocity is also increasing. And then does it become at smaller scale close to critical, like 1,000, or is it?
Okay, so you're asking questions about computations. People have done computations or experimentally.
It was those numbers. You're putting in.
But then
you're putting in energy in a scale, so you.
Yeah, I don't know what the prefactors are. So people have tried to sort of push this numerically, but I'm not going to be able to tell you, and I don't know what the prefactors.
No, I'm not asking about the number.
Yeah.
Is the idea is that this Kolmogorov length is the length at which the Reynolds number gets close to this minimum?
But close, because the Reynolds number, so you're asking the transition to turbulence, you mean? The problem with that question is that I have to specify a boundary value I have to specify a boundary condition. So the notion of a critical Reynolds number is detail dependent. Meaning that if I do an experiment to find out what the instability for transition is with a cylinder versus a sphere versus some other body, they all depend, the numbers are different. When you say critical Reynolds number, in this context, critical Reynolds number for what?
For your eddies. There's no solid there. It's a free, it's
yeah,
a isotropic fluid.
Yeah, so I guess I'm trying to understand the question because for eddies to form, I have to force it. And how should I think about?
Well, you're forcing it, you're putting energy in large scale.
Exactly.
And then it forms some eddies that have some local shear, local velocities.
Yeah.
That have some, you can define the Reynolds number because they have a length scale
Correct.
and velocity.
Correct.
And so, and it keeps decreasing.
Correct.
And so,
but you say critical Reynolds number, and that's an ill-defined notion until you tell me critical Reynolds number for what?
Critical maybe is a bad word. I'm saying is the Reynolds number cannot decrease forever.
Indeed, yeah.
So is that transition on some, this cutoff corresponds to this. If it's not molecular, it has to be something else.
Yeah, yeah. I'm not going to be able to answer that question now. I don't know. Yeah.
Where does the temperature come into play?
Oh, no. Temperature doesn't come into the play here at all. I mean, Phil's question was a liquid helium, and all the experiments there are pushing and asking the question about turbulence in a different setting. The different setting is associated with convection, with heat transport from one part of the liquid to another part. This, you're just driving it, and there is no temperature. Those two should be in different parts of your brain. Okay, so I have 10 minutes left. And I can either tell you something about free surface flows, or I can tell you about sponges. And maybe I'll tell you about sponges, because I've told you about sponges, at least I said I'll tell you about sponges more than once. So I won't tell you about free surface flows, instead I'll tell you about sponges. Okay? Because it's related to all the things, and again diffusion comes in, but diffusion of stress rather than diffusion of momentum, or diffusion of concentration, which you will see. Okay, so what is the motivation? The motivation is to think about fluid interpenetrating an elastic solid, you and me. Okay? And trying to ask what and how should we think about a system level description. And now, for the first time, I'm going to tell you that I want to introduce the notion of microstructure. So far I said I don't really care, we don't care. The fluid doesn't have particles that I actually have to worry about. I take a continuum picture, I blur my eyes so there are no details, there is no microscopic scale. So something which is again worth pointing out, that the Navier-Stokes equations have no length scale. They have viscosity, they have a density, but my velocity scale of course is from the outside. There is no length scale in the problem. Okay? Now therefore, if I think about a fluid in a sponge, in an elastic solid, there are many situations. I told you, you and me. You also see this in clays. You see this in colloidal particles which are able to interact with each other, for example, through depletion or because they are tethered polymers. And you see this in gels, many liquid penetrated gels. And so the question is, how do you describe it? Okay? So I have to now tell you about another specific limit of the Navier-Stokes equations. So Navier-Stokes equations, I'm going to drop inertia. And if I drop inertia, I have a balance between viscous forces and pressure gradient. And of course, I have incompressibility. And now, I'm going to ask you to think about this interpenetrating composite of solid plus liquid. Okay? So there's my liquid. This is a polymer network. It could be clay particles. I don't really care. So now I have at least one length scale. I could have many, depending on how complex this molecular microscopic structure is. And I'm going to call at least that one length scale the pore size. Okay. I, of course, have another length scale also, which is my system size. And I now want a description of this system, not on the scale of an individual pore, because then it's either a fluid or a solid, but on a scale which is large compared to the pore and small compared to the system. For you and me, that would be on scales depending on where you are. If you're inside a cell, cytoskeletal polymers interact with each other, cross-link and so on. The distance between cross-links is of the order of maybe 10, maybe 25, maybe 100 nanometers, depending on where you are in the cell. So I want a description, if you want, of the inside of a cell as a sponge, or I want a description of a number of cells with water in between. That's still different, but it still has this picture. Okay? And so we'd like a description on this scale. So I will first tell you about what's really driving the system, because I want to ask how many different scales there are and what can you actually say. Sponges, like the ones that you use in your kitchen, you basically are, you're going to squeeze it on a centimeter scale. Okay? If you have yogurt which is settling, you might have noticed, this is an experiment for you to try. If you take yogurt and you spoon out 1 spoon, and then you come back after you've eaten that spoon, 5 minutes later, you've seen that the depression is filled with water. I'm sure everybody's noticed that. If you haven't, don't do it tonight. Okay? The question is why? Why does it fill up with water? Okay? So it's someone leaking water. The Leaning Tower of Pisa is the other extreme. Leaning Tower of Pisa is leaning because it's essentially sitting in soggy land, but the land is not uniformly soggy. So it's starting to settle, but it's not settling like this, it's settling like this. Okay? So on the macro scale, on the micro scale, and the question is, how should I describe this? So I'm driving the system on the large scale. So I want to ask, what does this equation look like? So the left side looks like P over L system. I'm basically pushing on the large scale. But where is the dissipation occurring? Dissipation is occurring on the pore scale. Because on the pore, the liquid is stuck, and then this liquid just near it is moving relative to that pore. So all the dissipation is occurring on the micro scale, which means this side looks like mu u over L pore squared. And now, if I go back and look at this, rewrite this, this says that the pressure I've just rewritten. This, you recognize, is the local viscous stress. This is the pressure. The pressure is much larger than the local viscous stress because it's multiplied by system size instead by pore size. That means that in such a medium, the dominant contribution to the stress is the pressure, which is the same thing as saying that the stress is isotropic in the sponge locally. Okay? Because what really matters is force balance rather than stress balance. And force balance says that, in fact, the pressure is larger than the viscous stress by this amount, so the dominant contribution is just the pressure to the stress. So why is this relevant? Why is this important? This is relevant and important because I'm thinking about a sponge. The sponge, really, you can think about it as an electrical network where I have a bunch of holes, I'm driving fluid through these holes. The potential difference is the pressure, the resistance is the resistance of the pores, and the velocity is the current. And it's a linear relationship. Okay? And that linear relationship tells me that the pressure is related to the velocity, but it's related to the velocity. So if I write down this slightly differently, I can write down grad P is U, because dominant contribution is grad P. U is really U over H squared, pore size squared. So I can rewrite this as U is grad P times 1 over mu times pore squared. And I have to put a negative sign over here because if I take a Laplacian, I'm going to get a negative sign. Okay? This equation, which follows from the fact that I have a scale separation, can be naturally derived from the Stokes equations. And it's telling you something very, very nice and very simple. It says that the velocity is proportional to the gradient in pressure, and the concept of proportionality is what's called the hydraulic permeability. And depending on your persuasion, some people will write down K over mu, and others will just lump them together. But the most important thing that I want to emphasize is that this quantity, K perm, has some minimal information about the microstructure. It has the pore size built in. Okay? That's called Darcy's law. This law is called Darcy's law. Okay? It's the natural analog. If I have heat, I replace this by Q, I replace this by grad T, and then I have my conductivity over here. Okay? So it's every discipline has its linear laws named for the people who worked in that discipline. But this is the law in hydrodynamics for a relationship between flux or flow and pressure gradient. So Darcy's law.
But somehow it's also a reflection of losing Galilean invariance.
Absolutely. But that's good because I actually am moving relative to the solid matrix.
Right.
And I need to lose Galilean invariance. Exactly. Yeah. Thank you for pointing that out. Okay? So this equation then becomes much simpler. It's this plus this. Okay? That would be true if the porous medium was rigid. If the porous medium is not rigid, I just have to do the bookkeeping a little more carefully, because now this U is not the velocity of the liquid, it's the velocity of the liquid relative to the solid. That's all. But now there's a problem because I have to tell you what the velocity of the solid is. So I now have to self-consistently calculate both the motion of the solid and the liquid in a porous medium, which is soft. Because once I have U is grad P, I can just substitute this in this. Or I should just say that, I should probably do it as well. And then I'm going to get I know time's up. And that's an equation which, if the permeability is a constant, is a Laplacian of P, so it also tells you how to solve it. So you use all your standard tricks. But I can't do that, and if you give me Can I have 5 minutes? Okay. I want to show you what the equation looks like if I have a soft medium. So this is for the rigid medium. So what does it look like for a soft medium? Because U is no longer absolute velocity, it's relative velocity. Velocity of the fluid compared to the solid. Okay? So this will cooperate. Okay, so what did I want to say? So yeah, so how should I describe a soft porous medium? Let me say this because the next transparency I'll actually solve the problem for you completely, I think. So there are a few parameters in the problem. I'm going to assume that we are not operating the limit where the speed of sound is relevant at all. Speed of sound is solid. This liquid I'm going to assume is incompressible. That would only be true if I'm in a car crash. And hopefully I don't have to deal with that because before I solve an equation, other things will happen. So I'm in a funny limit. When I move when I move the liquid through the solid so slowly that the viscous forces don't deform the solid at all, a purely elastic description suffices. When I move the liquid through the solid very fast so that the solid can have waves, then I have viscous friction in the liquid, waves in the solid, so I have some sort of viscoelastic. And now I ask, what happens in between? Where are the dragons? What happens when I move from one limit to the other? And I'm going to call that theory poroelasticity. It was reinvented every 20 years. It was first done, I think, by Frankel in the context of earthquakes and liquefaction in the 1920s, then by Bio in 1940, then in 1960s by a whole bunch of people working at Terzaghi, who are earthquake engineers and seismologists in the 1960s, in the 1980s by people in soft condensed matter, and most recently, 2000, I think, Doi and people like that, both every 20 years, without knowing about this existence of the theory, have reinvented it. There are small variations. Okay? So this theory of poroelasticity operates in a regime where the frequency which you're driving is not too large and not too small. I won't belabor the point, but you can. And what I want to do is to go through a thought experiment and a little scaling argument. So the thought experiment is the following. I have my sponge. I have a piston. On top of the piston I put some weight. And the piston has holes which are large compared to the pores in the sponge so that water can move. And I want to describe the dynamics of this process. Okay? The reason I have an impermeable boundary everywhere else is because the only way the piston can move is if water moves through the piston. So it's one dimension. Very simple problem. Okay? The fluid volume fraction is phi. The solid volume fraction is 1 minus phi. The modulus of the network you can calculate. For example, I think in polymer physics you will learn how to calculate that as a function of the volume fraction of the polymers, but I'm going to assume that it's known. Now, I use the argument that I just told you. I start with Stokes, but I say, in fact, Stokes is going to reduce to Darcy. And I should, rather than gesticulate, use this pointer. Okay? So I now have to ask what is the balance of forces. So the stress in this continuum has two parts to it. The fluid stress is just proportional to the pressure, because of what I told you. I have weighted it, as you would do in a theory of mixtures, by the volume fraction of liquid. The solid has also got a stress, and that stress is proportional to the displacement gradient, the strain, multiplied by its modulus. Now what modulus should I be using here? I ran over this too quickly. It's the modulus associated with changes in volume. Because changes in shape do not necessarily cause the fluid to move relative to the solid. In order to get the liquid out of the sponge, I have to change the volume of the solid skeleton. Okay, so C is a dilatational modulus. And the balance of forces says divergence of sigma is equal to 0, so that's what I get. But that's not enough because I have two unknowns. Then I use first Darcy's law. Let me go here. Darcy's law says that the gradient in pressure is proportional to the velocity, but now it's the velocity of the liquid compared to the solid, because the solid can move too. And then finally, I have the equation of continuity. Okay, the fluid velocity and the solid velocity together are incompressible, but separately are not. This is a collective mode. The solid can be incompressible, the fluid can be incompressible. I put them together, and they are not incompressible. And this should smell like, for those in hard condensed matter of what a theory of superfluidity would look like, where you have normal fluid and superfluid, and then you have all these different sound speeds. And in fact, mathematically, there's a very beautiful analogy between this and second sound, in fact, it turns out. Okay, so I put all this together, and I will just focus on this one equation. So just a little bit of algebra, and I get a single equation for U, the displacement, which is what I was interested in. And I have a diffusion equation with a diffusivity, which you could have written down based on dimensional analysis. Okay? So I have a microscopic scale, which is the pore size. I have a viscosity of the intervening fluid, and I have an elastic modulus of the solid. From the modulus and the viscosity, I can construct a time scale. And then you might think it's viscoelastic. And that would be the case if you didn't worry about the microstructure. But I have to worry about the microstructure because fluid has to move relative to the solid. And so there is a diffusion constant. And the diffusion constant is the ratio of the elastic modulus divided by the viscosity multiplied by the permeability. The permeability is the pore size squared. What's the point of this? And I'll stop now. Overrun my time. The point of this is that for a typical fluid, water, this is 10 to the minus 3. For a typical solid like a sponge, K is of the order of 10 to the 3, 10 to the 4 pascals. So this time scale is of the order of 10 to the minus 7 seconds. So things would relax in a bare viscoelastic system very quickly. But K is very small also. It's 10 to the minus 6, a few microns. Which means that the characteristic length scale that I get, okay, remembering from this morning, a length scale from diffusion is square root of dt, or equivalently, a time scale is a macroscopic length scale divided by d, and the macroscopic scale can be centimeters. The microscopic scale is a micron, so I have 10 to the 4 squared, 10 to the 8, so I can get relaxation on the time scale of a second, even though the microscopic scale of time is 10 to the minus 7 seconds. Okay? So that basically is what's happening from the mathematical end. From the physical end, it's very simple to understand why it should be diffusive. I squeeze the sponge, liquid has to leave. If the sponge is very thin, it can leave very easily. But if the sponge is large, I have to move all the liquid from the interior all the way to the boundary. Very hard because lots of pores. So it becomes extremely slow. So you've changed this microscopic time scale, which is a ratio of a viscosity to an elasticity, by multiplying it by the scale of the system divided by the microscopic scale squared. So if I have scale separation, and in all these porous media that we normally think of, you have huge scale separation. Driving the system on the centimeter scale, dissipation on the micron scale, the actual time scale is 10 to the 8 to 10 to the 10 times the microscopic scale. And suddenly it becomes visible. Which is why your yogurt, even though the pore sizes are small, the distance over which the water moves has to be a centimeter. The water settles, comes out on time scales of seconds, tens of seconds, and even a minute. Okay? So, I want to show you one thing. You can essentially do experiments. These are experiments done in the Dave Waits group, where this was a fractal colloidal structure, but slightly denser than water, and with time, it just sedimented. It's the reverse of creaming. And if you look at the time scale over which this process occurs, and you plot it with the height, you find beautifully that the time goes as h squared, and the effective diffusivity is something that you can actually calculate this in process. So I'll stop here. I'm sorry I ran well over, but thank you.
In the polymer language, then another consequence of this was, for us, is strange, is that if I have a polymer solution without any, no liquid, you still have propagating shear loss.